Talk by Biswajit Karmakar is on quantum electron optics using quantum Hall edge states.
Thanks to the organizer for inviting me to give this talk. So it is a nice venue and I see a lot of students, they are attending. So it's like a not conference, more of a school. So I actually try to convince the students that we can do really some good thing even in India. And let's see over the years what our group and we have done in this subject, so that I'll explain step by steps in this talk. Okay. So first, this quantum Hall system, it basically doesn't require any introduction. It's already you have learned from the first days. These are these electron energy quantizations, Landau level, and if we do the transport experiments in a Hall bar, we see that at low magnetic field, this Hall voltage is linear, and at higher magnetic field, this Hall resistance is quantized. Okay, and whenever there is a quantum Hall plateau, then you have a longitudinal resistance is 0. So in this thing, basically each Landau level at the boundary forms kind of a edge states, and each edge actually contributes a Hall conductance E square by h, and magnetic field actually controls the number of field Landau level, which gives actually quantum Hall effect. So here, basically, what we want to point out that at the quantum Hall plateau, we see this resistance 0. This question is why this resistance is 0. So it is of course not superconductors. This 0 resistance is exponentially 0 with temperature. Okay, and there we say that edge states at the boundary, this Landau level is dispersive and it's carry current, and these are topologically protected states in the quantum Hall insulator, where Fermi energy stay at the bulk of the gap between the two Landau levels, either it is Coulomb gap or Landau level gap or Zeeman gap. So in this thing, this edge states, we can write free wave function as a wave function like a free wave. It's moved in y direction like a plane wave, and x direction it is localized like Gaussian wave. This is kind of a lowest Landau level function, and it has an orbit 0. One can write like this LB squared ky, and one can define this can be solved, or already you have solved probably in the class. So now if it is a free wave, then one can see the basically wave nature of the electrons. Like you have learned this in the Drude model, this electrons are particle, and you have worked out the theory. Even in this tube light, this thing, basically there is a atomic transition. Basically electron is going from one level to other. So you see the particle nature of the electron, or in the LED light. So basically electron in the conduction band, valence in and hole in the valence band, they recombine and gives photon. So you are getting the particle nature. So here basically when we are talking about the wave nature of electron, so one has to do kind of a interferometry. So this is the first experiment is done by Murthy Bloom's group. There basically this is the optical analog of a magenta interferometer. You split the beam with a beam splitter, and then again you actually this two beam actually meet at the beam splitter, and you have a detector 1 and detector 2, and you see this interference. So same thing actually, this is the schematic with at nu is equal to 1, there is only one electronic edge channel, and through the QPC, this acts as a beam splitter, it split the beam 50-50, and then you re-interfere at another quantum point contact, and then the whatever outgoing beam, it reaches to D1 and D2, it is actually analog to this optical Mach-Zehnder interferometer, and to the end, so this is the actual device picture of them, and one can see that there is a oscillation, current actually oscillates at detector D1. So in this experiment, what they have done, this is time. Basically what happened, this is a huge, large area and magnetic field is very high, 5-6 Tesla. What happened that in this loop area, there are huge magnetic field. If you sweep the magnetic field, so there will be, this oscillation will be fast. So they put the magnet in persistent mode, and there is a very slow decay of the magnetic field, and that changes slowly one flux quanta, and you will have complete one oscillation. On the other hand, one can actually tune this gate voltage so that you change this loop area. So this is the, again, it gives oscillation. You change the loop area, you change the flux in the loop. So this is the thing, and in this thing, visibility of an interferometer can be defined as Imax minus Imin divided by Imax plus Imin. So if your Imin is 0, then you will have 100% visibility. So in this thing, basically, it depends on how coherent is your beam. So you will see your visibility will be high. So in the first experiment, they have shown nearly 53% visibility, but after subsequent paper, they have shown visibility more than 90%, 96%, very high visibility. So now in this kind of interferometry actually does the rotation operation, and where this rotation, this theta is actually controlled by this change of magnetic flux. And this qubit rotation operation can be done this way. And there are a lot of proposals. So basically, this is one of the qubit operations one can do. And there are, subsequently, there are a lot of proposals. So in the in this thing, you see, this one of the beam is connected to the OMI contact, so you cannot use this beam. So, Giovannetti of Scuola Normale Pisa, he proposed this kind of Mach-Zehnder interferometer with co-propagating edge states. So where you set filling fraction nu is equal to 2, there are two edge modes, spin up and spin down. So they co-propagate, and you have a with beam mixture, you mix the beam, and then you create a area between the two edge mode where you introduce this magnetic flux, and then you remix here and you separately contact the output, and you can have a interferometer. So in this thing, so as I told you, this output beam is available for further processing, and one can have a very small loop, so we can sweep the magnetic field easily. So in this thing, the main difficulty is the beam mixture. If we consider the nu is equal to 2, it's a spin up and spin down states. So they are orthogonal eigenstate of Hamiltonian. So mixing of them is difficult, so they don't mix. So how we do that? So we have actually realized the mixing by Hamiltonian engineering. So basically, beside the let's say these are the spin up and spin down mode, and we place the nanomagnet, which actually put the in-plane magnetic field. So at resonance condition, so basically it flips the spin and mixes the beam. Okay, so this is the idea. So how we put the in-plane field? So this is the today is buried inside the sample, let's say 100 or 80 nanometer below the top surface, and we put the nanomagnet, and there is a fringing field, and you see at the below you will have a kind of a little bit tiny parallel magnetic field which is applied on the today. So that way we can actually put the parallel in-plane magnetic field that actually helps in flipping the spin. So as I told you that these edge modes are orthogonal. So basically this is the kind of free wave. So now if you take the overlap integral of these two, there is a physical overlap. I1, 2 is nearly 1. Their separation is very low, less than magnetic length, but their wave vector are different. So that's why there is a momentum difference, and they are spin orthogonal. So that's why they are orthogonal eigenstate of Hamiltonian. So they don't mix. So what we did actually with the nanomagnet, we put a periodic magnetic field in the parallel direction. So this has a periodicity of ky, and this k is the 2 pi by lambda periodicity of the nanomagnet, and this sigma xx actually helps here this spin down and spin out this matrix element become now unity. So spin orthogonality goes away, and with this ky gives a momentum kick, and that actually remove this orthogonality condition. To the end you have this. Okay, and when your delta k, basically k1 minus k2 is equal to k, equal to, then this sinc function goes to delta L, and to the end you can have a finite probability to flip the spin, and one can have a beam mixture. So this is purely Hamiltonian engineering. So this is a plot. So for different 2 pi by lambda different nanomagnet periodicity, we have, this is the experimental thing, how it mixes, and this is the kind of a theoretical plot, how the sinc function look like, and this actually matches, it gives kind of an idea, it is following whatever we have theoretically estimated. So, so now the question is whether it is coherent or incoherent, that we have to test. Okay, so now next we have actually made kind of an interferometer. So we put the nanomagnet to set up, and in between we put this gate to create kind of a loop area in this thing. So now we did, and in the previous experiment we found close to 400 nanometer periodicity. We have this maxima. So we put this 400 periodicity nanomagnets array, and this distance is like 6 micrometer, and periodicity is 400 nanometer. And with this configuration, if you actually sweep the magnetic field and with tuning the gate voltage, we see this oscillation. So it proves that this beam mixing is coherent, and it gives kind of a quantum oscillation, although the visibility is very poor, and this visibility actually goes down with increasing temperature. So this is the thing is done, and then theoretical simulation actually resembles our experimental data. So basically incorporating a dynamical phase variation with changing the gate voltage, we can actually simulate experimental results. Now, this is the thing we have done in the interferometry with electron. Now we are thinking about this anionic interferometer. Recently, from Manfra's groups, they have actually demonstrated this Fabry-Perot interferometer, and nu is equal to 1/3 states, and where they have observed this anionic oscillation and this braiding statistics. Where, so since it is Fabry-Perot, their visibility is quite poor. So one have to have a kind of a good fractional edge mode. Then one actually can make a good interferometer. And in this direction, recently we have done some work to prepare a good robust fractional edge modes. So this is the typical quantum Hall data over 0 to 30 Tesla magnetic field. And we see from 0 to 2 Tesla, this is 0 to 5 Tesla, we see that we have a very nice integer quantum Hall plateaus. And between 5 to nu is equal to 1, we see there are fractional states appearing. Then again, we see that integer quantum Hall effect nu is equal to 1 plateau comes, and at higher magnetic field, we see the fractional states all are coming. Basically, this Jain sequence is coming. So now the question is, we see at low magnetic field, this Coulomb energy is E square by LB. Since magnetic field is low, it doesn't matter. But at least above 5 Tesla magnetic field, we see that fractional states are coming. So that means Coulomb interaction is now start playing role. Then again, when we go into integer quantum Hall effect, we do, so this is an integer plateau, and integer plateau is explained by this conductance E square by H, like electrons is carrying current. And then again, if we increase magnetic field, again, it enters into fractional effect. So now so in this region, our question is whether what is electron-electron interaction is doing in these quantum Hall states. So this is the thing actually we want to explore. To do that, we have actually made a multi-terminal device in this geometry, where the two-terminal actually resistance shows this kind of quantum Hall plateau. We see nu is equal to 2 close to 5 Tesla, and then 8 to 11 Tesla, we have nu is equal to 1. Then again, we see there are structure, and we close 4 Tesla, we see 2 by 3rd plateau. And if we see the gate characteristics G1 or J2, so as we put negative bias voltage, then from this conductance, transmission conductance underneath the gate actually reaches from 1 to 2/3, then 1/3, and then goes to 0. And reflection conductance actually from 0 to it goes to 1/3, 2/3, and goes to 1. So that way we actually characterize the device. So basically, since our plateau is extended 8 to 11 Tesla, this is the interested region where we want to do these experiments. Here, this separation between the gate to gate is 125 micrometer. So now we have actually carried out this two-terminal conductance resistance measurement, two-terminal conductance measurement. Okay, so what we did, we actually measured the two-terminal conductance. We excite S1 and measure current at D1, or S1 we excite and measure current at D1. So that way we measure the conductance, and we can do simultaneously. So let's say we excite this thing at 17 Hertz and we excite this thing at 23 Hertz. So at a time when we do the experiment, we can record the data. Okay. And so this is the kind of, in the first experiment, nu1 we have fixed at 2/3, and then we sweep the gate voltage of nu2, this nu2 gate voltage. Okay, and in the at low magnetic field, what we see that this conductance S2 to D1 that increases, as also the other conductance. And if we actually add this blue and orange curve, you see this pink curve, it is like a normal gate characteristics of this nu2 gate. It reaches 1/3, 2/3, and 1. Okay, so but in the two-terminal conductance, what we see when this is 2/3 and this is 2/3, then 2/3 into 2/3, 4/9 is your conductance. Or if it is 2/3, it is 1/3, then it will be 2/3 into 1/3, so 2/9 your conductance. Okay, so now we have varied the magnetic field. As we go to higher magnetic field, so it deviates from this 4/9 or 2/9 value, but when at highest magnetic field, 10.9 Tesla, we see that there is a significant deviation. So as if this H2 to D1 conductance reaching towards 2/3, and when nu2 is 2/3, it goes to 2/3. When it is 1/3, it is 1/3. And from H1 to D1, we see it is going to 0. So this is a new limit we are actually getting. So in this thing, with the theorists we have discussed, and finally we have explained this thing with the edge reconstruction of nu is equal to 1 edge mode. And so what we are considering, that there are 3 edge mode which has a conductance 1/3, 1/3, 1/3. So total conductance will be then 1. And in this thing, the outer 2 mode, so those are similar, like 2/3 conductance and like 2/3 edge states. So there are 2 edge mode which has a very low equilibration length, and they goes from S2 to D1. And this other mode, this red mode, which has a 1/3 conductance, but we are considering that low field, it has a low equilibration length. At high field, they are decoupled from the other 2. So this is the model we have considered and try to explain our data. So when actually we have a conductance, we have a gate voltage 2/3 and 2/3, and at high field, this red channel completely reflects back to D2, then this 2/3 mode enters in the propagating region and reaches D1. So we'll have a 2/3 conductance that we see here. And from S1 to D1, so nothing will reach here. So you see 0 limit. Okay. And when actually we put the filling fraction 1/3 here, you see 2/3 current here, and then half of this thing reflect back to D2, and half of that goes here. So we'll have a conductance 1/3. So that we see, and from S to D1, we see 0 again. And when at low field, so basically all the edge modes equilibrate, so we see this normal conductance as well. So with this model, actually we can explain this this experimental data. So now we actually we can corroborate our model by putting the filling fraction, this new one, the fast gate at 1/3, and we do again the same experiment. We see there is a new plateau 1/3. So what happened? This 1/3 mode goes and they equilibrate, and finally all the current actually reaches to D1. So ultimately you will have a conductance 1/3 that we see here. Okay, and from reaches to 1/3, and from S1 there is a 1/3 mode going, and they equilibrate again reaches to D1. So again it reaches 1/3. But if we put the filling fraction 1/3 here, then they equilibrate and half of the current goes. So you will have a conductance 1/6. So this is the kind of, that way actually we explain all a set of data, whatever we got. So now we did actually temperature dependence of this conductance, and we see this conductance basically as we increase the magnetic field, this goes down, and with simple stochastic process, equilibration process, we actually define some equilibration length, and if we feed the data, we see that this red mode, which have an equilibration length at low magnetic field is very low, but at high magnetic field it goes as high as close to millimeter. So this is so this is the key result. So if equilibration length is of order of millimeter, then actually it's robust and it doesn't interact with the. So basically, so this is the thing one can use for this Mach-Zehnder interferometry. So you have a robust mode. And robust mode. So another thing is that, as we said, that this outer two mode, their equilibration is very low, but we put the magnetic field now at 14 Tesla, which has a filling fraction 2/3, only two mode is there. And in this two mode, again, when if they equilibrate properly, then you will have a 1/6 conductance. But we see there is a deviation. And from this deviation, we can calculate this equilibration length, something like close to 100 micrometers. So again, since it is a long wavelength, one can actually utilize this kind of mode for this anionic interferometer. So in 2020, we have done this experiment, and after that COVID came and our nano device, this fabrication facility got derailed. So we could not do much progress. So we are doing some other work, but I'm not disappointed and I'll not disappoint you. So basically from Murthy Heibloom's group, now the anionic Mach-Zehnder interferometer come up in this year. So what they did, so basically this is the sample close to 5 Tesla 2/3. They measured this equilibration of 1/3 mode has a equilibration length something like 234 micron. And Professor Gefen is the theorist in that. He also analyzed, he looked those kind of data. So now they have done the experiment at 2/5, where there is an outer 1/3 mode, which actually interaction free at 12.5 Tesla. They did this Mach-Zehnder interferometry in this device, and they published recently, and they could see with 22% visibility, very nice anionic interferometry, and they are breeding. So now, basically now we have understand we could contribute something towards the electron interferometry. Now we know about how to prepare this anionic robust states. So we could actually take this kind of interferometer. We can make series of concatenated interferometers or two photon interferometers, which propose for integer geometry. Those we can actually apply for anionic system. Also, there are some proposal how one can study the CHSS inequality by this low frequency cross-correlated noise. So those things can be extended in anionic interferometry. So we are looking forward to this kind of experiment. So with this, I thank my collaborators. These are the students, and they are the experimental collaborators, and we have theoretical collaborators. So with this, I thank you.
Thank you very much. I would like to begin with two comments.
Yeah.
One comment is that you cannot say that a chiral mode of 1 consists of 3 chiral modes of 1/3, because that will give you the wrong topological number. In other words, in the right units, the heat conductance of 3 1/3 modes will be 3, while a single mode will give you heat conductance of 1. And similarly, you cannot say that the 2/3 comprises 2 modes of 1/3, because that will give you heat conductance of 2, while the heat conductance of 2/3 is 0. So
Yeah.
you need to be very careful.
Yeah,
about
yeah.
that.
So in this thing, yeah. So basically, whatever, so our point is we are doing very simple measurements of charge transport. Okay. So in this thing, we cannot actually measure neutral mode, or even it is quasi-partially taking transport, or the quasi-whole event. So those kind of answer we haven't. So our point is, so I'm correcting myself, whatever we have seen that, so there could be other mode is there, could be not, it is there, but we cannot detect from our experiment. But it is there.
No, but it's not three co-propagating modes. This cannot be the case for one, because it's a different,
yeah, there is
topological
heat
number.
conductance thing. So basically there are other parallel modes, and it has to, for nu is equal to 1, so heat conductance would be 1, and it has to match.
And the second comment is that in the very first part of your talk, you said you talked about mode mixing with different spins. And the idea is that, if I understand correctly, is that you want to rotate the spin.
Flip.
Or flip, rotate. But if you want to see rotation of spin, you don't need to go to nu equals 2. It's enough to have interferometer of nu equals 1, where one reference mode remains unchanged. The other reference mode has a spin rotated. And then you can see that depending on whether you did or did not rotate the spin, the interference of the two modes will be strong or will be weak or may even be 0. You don't need to go to nu equals 2.
Okay, so this experiment, one has to think and one has to perform this kind of experiment. Thank you for your input.
Now, questions? Any questions? Yes.